Hello everyone, welcome back to Introduction to Data Science Part 2, presented by me. This is table of contents for today. First, what is data preprocessing? And beside from that are all typical techniques used in data preprocessing. So first, what is data preprocessing? Data preprocessing is the process of preparing raw data for analysis by cleaning and transforming into a suitable format. At the image on the right-hand side, this is the process of data preprocessing. First, we have data cleaning that identifies and correct error in data set, data integration, which means that merging data from various sources into a single unit. Another one is data transformation, that converting data into a suitable for analysis. And the last one is data reduction, that reuse the data set size while maintaining the key information. So now let's move to aggregation, which is the processing of combining two or more objects into a single attribute or object. For its purpose, first, it data reduction, it decreases the number of attributes or objects. Another one, chain of scale, which is allow data to be viewed at a higher level. For example, cities aggregated into regions, states, countries, and more. Lastly, more stable dataset, which is that aggregated data tend to have less variability, which means that it's a way of reduce the effectiveness of random noise. So now let's move to the next page, which is the example of aggregation. These two graphs illustrate how precipitation varies in Australia. So as you can see, the picture on the left-hand side, yes, X stands for standard deviation, is the unit of monthly landfall variable, and Y-axis is represent for number of land location. When we do that on monthly basis, we got this very wide spread of standard deviation. Some places are very consistent in the rainfall and have this long tail, yeah, the long tail of the places that are just all over the place in terms of variability. In the other hand, which is in the right hand side, if we take those exact sample location and use aggregation, we can see the big difference, which is very small, very clean, and very short tail of histogram. So we have reduced the range of noise in the dataset by increasing the scale by aggregating data. So that's one of the reasons that we use aggregation. Now let's move furthermore to sampling. The definition of sampling is the process of selecting smaller subsets of data from larger dataset while still keeping the important essential characteristic of original data. So why we use this? Because analyzing the entire datasets may be too expensive, too slow, and unnecessary. This is types of sampling. We have four types. First, sample random sampling. Example like there is an equal probability of selecting any particular item, which means that every member of population has the same chance to be chosen. Another one is sampling without replacement. As each item is selected, it is removed from population. That means that no item can be selected more than one in the same sampling. Next, sampling with replacement. Objects are not removed from the population as they are selected from the sample, which means the sample object can be picked more than one. Last, stratified sampling, which is split the data into several partitions, then draw random samples from each partition. It ensures representation from each subgroup of the population. This is the example of sampling. Sampling density is really matters because of more sampling can be points or dots produce a clearer image. As you can see the first image that has 8,000 points, we can see the image really clear and very detailed. And if we use some points to 2,000 points, the image is still recognized because of some structure still remains. And if we still use it into 500 points, the shape becomes rough and hard to distinguish. Next, let's move to dimensionality reduction. It's the process of reducing the number of input variables in the dataset while preserving as much important information as possible. In the other word, which means that instead of working with hundreds or thousands of features, we transform into data into a smaller feature space that still capture the essence of the original dataset. The purpose: first, it has a what's called of dimensionality, reduce amount of type and memory, allow easier visualization, eliminate irrelevant features, and reduce noise. For the techniques that we use with dimensionality reduction, it has principal component analysis, which is PCA, secular value decomposition, SPD, and other techniques like supervised techniques, nonlinear techniques, and deep learning approaches. This is the example of dimensionality reduction. In the first image, you can see that it has a higher dimension, which is 206. We can see the image look really sharp and recognizable. But if we decrease the dimension into 150, the image become blurred, but we still recognize that this is a person. It has a really lower dimension, which is 60. We don't even know that whether this is a person or a thing, a fruit, because the fine information is already lost. So now let's move furthermore to feature subset selection. So what is it? It is selecting only the most relevant feature and remove those that are not related. Why? Because too many features it causes slower algorithm and it can make risk of overfitting and cause of dimensionality. So let me explain. Too many features, it means like when a dataset has a very large number of features, attributes, or column, the problem is arrest. And slow algorithm, it means most algorithms have a time complexity that grow with the number of features. And risk of overfitting with many features, the model can memorize noise instead of learning pattern. Lastly, curse of dimensionality. This is fundamental issues in a high-dimensional data that make the distance between less meaningful and visualization difficulty, which can easily interpret. And this is feature subset selection. For the purpose, it avoids the curse of dimensionality that too many features can confuse the model and require a lot of data. For improved performance, it's faster training, less memorized, and simple models. And lastly, better interpretability, it's easier to explain. In short, choosing the best feature from what you already have. As you can see in this example, if we predict the disease, age, blood pressure, and cholesterol are highly correlated, but patient ID isn't, so that removes the patient ID. And this one is feature creation. This is create new attributes that capture the important information in a dataset more efficiently than the original raw data. Instead of just using raw feature, it means that you can generate new one that make the pattern more visible to machine learning model. And this is three general methodologies. It has feature extraction, a domain specific, mapping data into new space, and feature construction that combine feature. Not only that, we also have discretization and binarization. So first, discretization, it converts continuous feature into a finite number of interval or category. As you can see in this example, this is the exam score that has from 0 to 100. So if you got 78, it will move to good. And the next one is binarization. It's converted data into binary value, 0 or 1, true or false, or it's like turning feature into yes or no or on or off switch. As in this example, exam score. If the score greater than 50, it will be 1, which is pass, and less than 50, it will be 0, which is fail. So next, let's dive deeper into similarity and dissimilarity. So in the left-hand side is similarity, which is a value that quantifies how alike of two objects are, which is this defines similarity as a numeric measure of how similar two objects are. And typically, similarity metric yield a score between 0 and 1, where 0 means no similarity, which is completely different, and 1 means like it's perfect similarity. For high similarity, it makes the objects are close in natural. When the similarity score is high, the objects are considered very similar or close to the same category. As in this example, two users who both like the same movie have high similarity, which means that the user with similar tastes, same movie preferences, are deemed highly similar. So on the right hand side, which is dissimilarity. So dissimilarity is the numeric measure of how different of two objects are. Dissimilarity scores start at 0, where objects are identical and can grow without both as objects become more different. For lower, when objects are more alike, which is asimilarity increase, the objects are more alike, which means dissimilarity is decreased. As for example, age difference between two customers, the age gap between customers is a dissimilarity measure. The bigger the gap, the more dissimilar. And this is Euclidean distance. It's a measure of how far apart two points are in n-dimensional space. This is the formula of Euclidean distance, where n is the number of dimensions, like attributes or features. Pk and Qk are the key component features of object P and Q, and in this case, standard deviation is necessary if scale differ, which means that if the feature have different units or scales, one feature can dominate the distance. So now let's move to Minkowski distance. It's a generalization of Euclidean distance, and this is its formula, where R is a parameter, N is the number of dimensions, and Pk and Qk are representative the key attributes, or can be data object of P and Q. Common properties of similarity. Similarities also have some well-known properties like maximum similarity only if P equal Q, and symmetry, which is the similarity from P to Q is the same as from Q to P, which makes sense when similarity is a measure of how alike two objects are. And next is cosine similarity. Cosine similarity is a measure the angle between two vectors in n-dimension space. It is often used for text or high-dimension data. If D1 and D2 are two document vectors, then we get this formula, where dot indicates vector dot products and D is the length of vector D. And here the example below you can see by yourself. And then this is density. It's referred to how much data point accumulate in a given space. Example, Euclidean density. Euclideicity is a number of points per unit volume, and probability density is describe how likely data points are to linear origins to the space. And graph density is the density derived from a graph representation of the data. And that's it for today's lesson. See you later. Goodbye.